Energy is conserved. Momentum is conserved. Angular momentum is conserved. A planet keeps orbiting. A pendulum keeps swinging. Colliding objects keep exchanging momentum. A rotating system keeps turning around a persistent axis. Physics is filled with quantities that refuse to change. But why these quantities? They are all consequences of symmetry. This story begins in Göttingen. Hilbert and Klein drew Emmy Noether into a conservation problem raised by Einstein's new theory of gravity. In 1918, Noether found that this technical difficulty was pointing toward a much larger principle. She would become one of the architects of modern algebra, and this theorem permanently changed theoretical physics. A symmetry is not merely a transformation. It is a transformation that leaves something unchanged. The square changes orientation, yet remains the same square. The triangle permits fewer rotations, and the circle permits infinitely many. A symmetry is change without observable change. Now move from geometry to physics. Slide the entire experiment 1 meter to the right. The pendulum keeps swinging exactly as before. Rotate the laboratory. The floor, pivot, and pendulum rotate together, while the pendulum keeps swinging inside that rotated frame. Or begin the same experiment 1 hour later. Different descriptions, same physical law. Could these symmetries explain the conservation laws? Imagine throwing a ball between two fixed events. There are infinitely many conceivable paths connecting the same beginning and end. The action gives every possible path a number. It is the time integral of a function called the Lagrangian. The square brackets around S of Q matter. The input is not one position, but an entire function of time. The action is therefore a functional, a machine whose inputs are paths. Nature follows a path for which the action is stationary. That does not mean the action is always the smallest. It means every sufficiently small change of the path changes the action only at second order or higher. The first derivative in every admissible direction vanishes. A valley works. A hilltop can work. Even a saddle can work. That distinction is essential. Nature is not commanded to choose the globally smallest action. Stationary action is the accurate statement. In ordinary particle mechanics, a common Lagrangian is kinetic energy minus potential energy. As the cart descends, potential energy falls and kinetic energy rises. As it climbs, the exchange reverses. Their sum may remain fixed while their difference changes. The Lagrangian is not itself the conserved energy. It is the local ingredient whose integral controls the allowed trajectory. And kinetic minus potential energy is only one important form. Field theories use more general Lagrangians. Take the physical path q of t and compare it with a nearby path. Write the nearby path as q plus epsilon times eta. The endpoints are fixed, so eta vanishes at the beginning and the end. Between them, eta may bend the path almost however we like. Assume the Lagrangian has continuous first derivatives and enough additional smoothness along the physical path for the time derivative below to exist. Also assume q and the admissible variations are differentiable, with the physical path regular enough to satisfy the resulting differential equation. Insert the varied path into the action. Stationarity means that the derivative of this action with respect to epsilon vanishes at epsilon equals 0. Differentiate under the integral. The multivariable chain rule produces two contributions. Changing the path changes q itself, giving partial L over partial q times eta. It also changes the velocity, giving partial L over partial q dot times eta dot. Integrate the eta dot term by parts. This moves the time derivative from eta onto the generalized momentum, partial L over partial q dot. The boundary contribution vanishes because eta is 0 at both fixed endpoints. After integration by parts, the entire first-order change is the integral of one coefficient times eta. The variation eta is otherwise arbitrary inside the interval. If the coefficient were positive near some time, we could choose eta supported in that region and make the integral positive. If it were negative, we could choose eta with the opposite sign. The fundamental lemma formalizes this reasoning. If the integral vanishes for every admissible eta, the coefficient must vanish at every time. And that forces the Euler-Lagrange equation. It is not magic. It is the mathematical form of stationary action. Shift the entire experiment forward in time. If the Lagrangian has no explicit dependence on the clock reading, the rule governing the motion is unchanged. Define E as q dot times partial L over partial q dot minus L. Differentiate E along the physical motion. Every term must be differentiated because q and q dot both change with time. Then expand the total time derivative of L by the multivariable chain rule, including any explicit dependence on the clock variable t. The q double dot terms cancel. The Euler-Lagrange equation makes the expression in parentheses vanish. What remains is minus the explicit time derivative of L. If L has no explicit time dependence, E is constant. For the standard mechanical Lagrangian with kinetic energy quadratic in the velocities, Euler's homogeneity relation makes q dot times partial L over partial q dot equal twice the kinetic energy. Subtracting L then gives kinetic plus potential energy. Time translation symmetry becomes energy conservation. Now shift the entire experiment through space. If the Lagrangian does not depend explicitly on a coordinate qi, that coordinate is called cyclic. The Euler-Lagrange equation says that partial L over partial q dot I is constant. This is the generalized momentum conjugate to qi. The coordinate could be a Cartesian distance, an angle, or any variable that labels the system's configuration. For a free particle, the generalized momentum is the familiar mv. The puck keeps gliding with the same momentum vector. Space translation symmetry becomes linear momentum conservation. Consider a particle moving in a central force. Rotate the entire system through a small angle. Nothing observable changes. An infinitesimal rotation moves r by epsilon times omega cross r. The corresponding Noether quantity is p dot that displacement. The scalar triple product identity rewrites it as omega dot r cross p. Because the rotation axis omega is arbitrary, the vector r cross p is conserved. The particle keeps orbiting, while the angular momentum direction remains fixed. The three examples share one mechanism. A continuous symmetry is a smooth family of transformations labeled by a small parameter epsilon. For a transformation that does not shift time, write the infinitesimal change as epsilon times x. If the Lagrangian is invariant, its variation can be rewritten using the Euler-Lagrange equation as a total time derivative. If the symmetry makes delta L 0, the derivative of p dot x is 0. That is the conserved Noether quantity. More generally, a symmetry may shift time or change the Lagrangian by a total derivative. The conserved expression is then modified, but the logical architecture is unchanged. For every continuous differentiable symmetry of the action, there is a corresponding conservation law. Noether's theorem is not confined to particles. A field assigns physical data to every point in space and time. For a global continuous symmetry, the natural conserved object is a current J mu satisfying a continuity equation. The equation says that charge cannot disappear locally. It can only flow from one region into another. Under suitable boundary conditions, integrating the time component over all space produces a conserved total charge. Gauge symmetries are not merely ordinary symmetries with more parameters. Their parameters may vary from point to point, which means some apparent changes represent redundancy in our description. Their consequences include differential identities among the field equations and are described more fully by Noether's second theorem. The same architecture now runs through electromagnetism, general relativity, quantum field theory, and the Standard Model. Noether arrived in Göttingen in 1915, where Hilbert and Klein were wrestling with conservation in Einstein's general relativity. Her 1918 paper proved two theorems. The first connects continuous global symmetries with conserved currents. The second explains the identities created by local gauge freedom. The reversal was permanent. Energy, momentum, and angular momentum no longer looked like unrelated rules. They became shadows of invariance. Return to the quantities from the beginning. Time translation gives energy. Space translation gives momentum. Rotation gives angular momentum. For centuries, conservation laws seemed like isolated facts about nature. Emmy Noether revealed that they were all shadows cast by symmetry. The conserved quantities are visible traces of transformations that leave the action unchanged. Symmetry is not merely beauty. It is the architecture of physical law.